Hello, everyone. I have not been replaced by a robot yet, though. Um, Hopefully soon. I'm tired. But I'm still real. I'm still trying to teach. You've got a picture of me now and a picture of the document camera. And the idea is that we're going to go through a couple of problems so that we can reason out some two-dimensional motion stuff. It's been a long week. I don't want you to worry about due dates. I'd rather you understand the stuff. That said, is you should expect that when you get the next packet of information, there should probably be an assessment in there that you need to do. And it's going to be on the vectors, the one and the two-dimensional motion, and maybe the circular motion. Because I'm hoping next week when you start that, you'll find that it's easy compared to everything else. That there's really not that much change in doing two-dimensional motion and in circles. It's more when you do arbitrary motion. So that said, it is a little tiring here, but we will, do a couple problems so that you have some examples, and so you can keep working. And some of you, I'm glad that you went ahead and been particularly independent because it certainly helps. And I'm hoping to hear from some of you that I haven't heard from yet because it's been at least 3 weeks now. So hang in there. Let's do some problems. All right, let's see if this actually changes. So you should just have the image here. And I'm going to tell you a story. This story involves cows. I used to have a farm, and let's put some cows in, some happy little purple cows. Which also suspiciously look like the deer that I drew once upon a time in another video. So I hope you can see that. Let's zoom in a bit and let's autofocus. Can y'all see that? All right, there's some deer on the screen. I'm going to get some markers out because the ink pens are not working as well as I like. We'll see if markers do better. So I want you to imagine you're a farmer in North Dakota. I obviously never was, but you could imagine that you've got a farm you're taking care of, and you're living out in the middle of nowhere, and suddenly blizzard happens. And so the ground's covered in snow. You've got to feed these cows, and you can't get in on the roads because the roads are blocked up. And, farms out there are kind of big. You kind of have to be able to drive around a bit. A couple of farmers had this innovative idea of bombing them with hay. They get a plane. All right, I even, note that I didn't draw the wings through the plane. There's a tail. And so what they're going to do is release a package of hay, a pallet of bales or something. And we can put some distances in here. Right? Let's say that the plane is flying 1,000 meters above the ground, which is, 3,000 feet. That's pretty low, but that's not like scraping the ground low. And let's also say that the plane is flying a reasonable speed, say 250 meters a second. Right? This is through the air, but it's relative to the ground, and we'll have to talk about relative velocities at some point. That's a week 4 thing. But the idea is that is going to be the speed of the hay bale when it leaves the plane. And so we'll also put that in the x-hat direction. Right? So in yellow here, in orange here, I'm going to put in axes, because in any good picture, you should put in axes, and this will be plus y, and I thought there was something wrong with the camera, but it turns out that there's something on my screen. And plus X. So we just put setting up as positive and toward the cows as positive here. Now what this bale is going to do, it's not going to fall straight down because it has this velocity. The first little bit of motion is like that, but then it falls, and the next little bit's like that, and the third little bit turns even more, and eventually it gets to the cows, to the herd. All right, and so the herd's sitting over here, and it can't really wander through the snow that well. So you kind of have to get as close as you can to it. And so this is a variable distance from the point of the plane to the herd. We'll call that delta x. And we'll set our coordinates over here as x equals 0. So we can ask, how early does the plane have to release the hay so that it gets as close as possible to the cows? All right, and obviously you're not trying to hit the cows, but we're just going to ballpark it as get it close, calculate the range that you would need to hit it, and then, do it a second or two early and it'll be correct. All right, so we want to know how far ahead we have to do this. So that's kind of drawn our picture out. And let's say that we also want to know a couple of other things. So one thing we want to know is delta x. What delta x do we need to make this work? All right, I keep trying this autofocus and it's not working. I don't know why. There, that's a little better. So hopefully you saw that a little better and you can see the picture here. So we've got this delta x, but we also want to know the direction of the hay at the ground. Let's just say that we don't want it to hit perfectly smushed flat, as if you just dropped it from a vertical, we don't want it to do that. We want it to do kind of that rolling thing. We want it to spread out. So we'd like to know that we're hitting the ground at an angle, and we'd like to know what it is. And that's going to be guaranteed by what's going on here, is that this will never get perfectly vertical. But you might want it to be a shallow angle instead of a steep angle. And that means you got to adjust your heights and your speeds. So these are the things we want. Now, what this really means is finding the final velocity vector so that we know the direction. But there's an important bit about this. Most of my students at some point have this conception that when an object hits the ground, well, now it's on the ground and it's not moving on the ground, so the velocity is 0. But the question is, how did it get to the ground? It started from some higher point. That means it had some velocity before it hit the ground. And so when we say what is the velocity at the ground, we mean just before it hits the ground, all right, the instant before. It's really, really close, but it cannot be v final. It cannot be 0. There's no way it can be 0. Because it's going to have some velocity at the beginning, and this can never change. It's got to have at least this 250 meters per second. Now, we're also making some other assumptions. No air resistance. It's not that we couldn't do it with air resistance, but we want to talk about forces before we bring up air resistance. Right? What we want is for this thing to be in free fall. That's important. Right? So what we're going to do is organize our information a bit. So I'm going to try to zoom out so you can see a little more video. Maybe bring, yeah, there we go. Now we can see the whole paper. All right. So what we want to do is organize our information here. All right. And if you remember the sorts of problems that we did in previous videos, let me pause for a moment and make sure. Okay, so remember from the third 1D motion video, if you've watched that, we did two things moving at the same time. And effectively, that's what we've got going on. We've got a hay bale that is falling, and then a hay bale that is moving in the x direction. So we want to keep track of two sets of motion here. And so what I'm going to do is say we have x direction, and then we have y direction. And we're going to keep track of those motions separately. So in the x direction, things are fairly straightforward. We don't know what delta x is. We can just call it delta x for the moment. But we know what v initial x is. Right, now we're putting in that it's in the x direction. We're going to distinguish it later from the y direction over here. And we know this is 250 meters per second. Now, we know what v final x is, because by the definition of free fall, gravity is only acting on the bale, and it is downwards. So there is no acceleration in the x direction. That's four variables. The fifth one we need is the time, and we don't know what that is. We have no idea what that is at the moment. So what we do is we go to the y direction info, and here is where we know some stuff. So to be clear, we're going to say that y equals 0 occurs at the ground. And so y equals 1,000 meters up at the top. And so when we say delta y, that is y final minus y initial. That is 0 minus 1,000 meters. So it's negative 1,000 meters. That's the important bit. We have to keep the correct sign on this to imply the correct motion. If we say up is positive and the bale is falling, it has to be moving with a negative displacement. Okay, so v initial y is going to be 0, and that's because the initial velocity only has an x component. So the y component has to be 0. In a one-dimensional motion problem, this would be released or dropped from rest. In a 2D motion problem, it's coming under the idea that this is a level flight, and then when we release it, the bale only has x direction motion to start with. Now, we don't know what v final y is, but we need that in order to get this direction question. We do know the acceleration in the y direction. One, because we just said that it's in free fall. The only thing happening is the gravitational acceleration. And two, we can make an assumption about the problem that if we're feeding cows with hay, we're probably on Earth. So we know that this is minus 9.8 meters per second squared. The minus is because, again, we took up as positive, and the vector g, the gravitational acceleration, is downwards. And now we have the time, and we don't know what the time is. But we're going to solve this problem in the same way that we solved the two things moving problem. When the thing hits the ground, it will have traveled the x distance in exactly the same amount of time as it traveled the y distance. Right? Is at any particular point on this curve that I've sketched in arrows, there is one unique time that that point shares. And so there's one unique time on the ground, and it's common amongst both of these. So now we can look at this. This is a problem because out of our four equations that we have, which now is 8, and I'll write these up over here, we have delta x equals v initial x t plus 1/2 ax t squared. We have delta x is 1/2 v initial x plus v final x t. That's just our average velocity. We have v final x is v initial x plus axt. That's our velocity equation of motion. And then we have v final x squared is v initial x squared plus 2ax delta x. That's our relation between velocity and position without time. And now, of all of these, we can also write 4 down that just change x to y. So if we look at these in the x direction, if this is what we know, if an acceleration in the x direction is 0, all of these things simplify to the same sort of equation. Delta x is vxt, or v final x is v initial x. They all simplify down to the same two assumptions. All right, one simplifies one way, one simplifies the other. So that said, although we seem to have 3 bits of information here, they're redundant. We really only have one, is the initial velocity. And so that's not enough to solve anything over here. We have to look at our y direction information. And here we have 3 bits of information: the distance, the initial velocity, and the acceleration. And the goal is to get to time, and that's usually your goal. If you're missing the time, you should probably try to find the time. And if you're missing the initial velocity, you should probably try to find the initial velocity. That's what we're working with. So we have this laid out. We look at the things, and the relationship between the initial velocity, the position, the acceleration, and the time ends up being this first equation up here. And so we'll work with that. Delta y is v initial in the y direction, t plus 1/2 a in the y direction, t squared. Now we realize this is going to be a quadratic of some sort. We got t's everywhere, right? So what we're going to do is go ahead and plug in our information. We have minus 1,000 meters is 0 meters per second times t plus 1/2 minus 9.8 meters per second squared times t squared. And that's the very nice bit about not having to throw this object down or throw it upwards. This term just goes away. Put that in a nice vivid color. Yoink. It's gone. And so this simplifies down a bit more. All right, is that we have a common minus sign on both sides, and we can rearrange this. But ultimately, it's going to be t is square root of 2 times 1,000 meters over 9.8 meters per second squared. And inside of this, we'll have meters canceling. We'll have 1 over second squared. That converts to second squared. We take the square root, and we'll have the time. And this is plus or minus. All right, so we'll have t equals plus or minus, and then we'll do the calculation. 2,000 divided by 9.8 is a big number, and we take the square root. 14.29 seconds. Now everything here is like 2 sig figs or less, but we're going to keep a lot of sig figs until we get an answer. So there is a question as to which time do we take, and it should be obvious that if the plane is releasing at t equals 0, we should probably take the positive one. The negative one would represent the cows throwing the hay bale up to the plane, or a mirror image of the cows off to the screen, over here, throwing the bale up to, so that, right, the math that we're drawing is just describing a parabola. And it doesn't have an idea of the beginning of the parabola being where the airplane is, because it's just math. So we translate it, and we know that it's going to be plus 14.3 seconds. So we can use that to get the position now. because now we have new information. We can plug in over here, hey, this is 14.3 seconds. And we can plug that in over here when we want v final y. All right, so I plug that in red. And now, right, so I'll move this down so you can see some more. We'll look at this and we'll say, hey, we can get delta x now because we have 2 bits of information we just need. All right, your full equation would be delta x is v initial xt plus 1/2 ax t squared. In general, these equations, this equation of motion for position, is the most useful. And we can automatically say that this term is 0 because the acceleration is 0. So this is just going to end up being 250 meters per second times 14.3 seconds. And this is still going to be 2 sig figs, but we take our original answer and we just multiply by 250. And we get 3,570 meters. Seconds cancel out. 3.6 kilometers. All right, and if you're familiar, 3.6 times 5 divided by 8 is 2.5 miles, just so you know. So in your mind, if you're designing an airdrop, right, this doesn't have to be to cows in North Dakota. This could be to starving Berliners in 1960 or 55 or whenever the airlift occurred. I can't remember. Or it could be to, it could be any sort of airdrop that you need to do. If you remember the famous movie Operation Dumbo Drop, where they dropped an elephant out of an airplane, I think it was by accident. I've never seen it. It's just a famous bad movie. I'm not even sure if it's bad. Anything could be planned like this. And now if you're planning it for an airplane, what you're going to do is say, drop it 14.3 seconds before we're over the target, and it should hit the target. Right. You're not going to say, drop it 3.6 kilometers, because you might not be able to see that visually what it looks like. You might have perception issues. But at least we have this, and then we can get to the second part. We want the final velocity component so we can figure out the direction. And this is a thing that students have trouble with, is the motion of the hay bale, the motion of an object. All right, we have this picture here, and what a lot of students tend to do is they go and they say, well, I have some motion, delta y, and I have some other motion, delta x. Right? Now, what they tend to do is say, hey, I have 2 sides of a right triangle. I should just put in the hypotenuse. And then this angle, theta, is what they claim to want. But that's not what's happening here. Instead, we have a parabolic motion. And so there's an additional angle. And so you have to be careful of this, right? The collision vector in green there is completely different from this collision vector in blue. I hope you can see that. Okay. So the thing to do is direction of motion is always velocity. It never has anything to do with the positions or the accelerations. If you're looking at the velocity at a particular instant, it tells you where the thing is headed in the next instant. So that said, we can go in now. We have, actually I need that picture out. What we need here, I've got a little bit of lack of room. It's kind of issue. right? But we have our y direction stuff. We want v final y. And now that we have the time, there's a lot of different ways we can go about this. The general principle is to stick with your original information if you can. And that would mean the things that we knew from the problem is delta y, acceleration, and v initial. And so we could do v final squared is v initial squared plus 2a y delta y. And that's going to be 0 plus 2 times minus 9.8 meters per second. And now you're looking at that minus and you're thinking, oh no, I'm going to have to take a square root of a minus. It's got to cancel out. You've got to have a positive square. And so what you'll end up with is minus 1,000 meters there. And so what we should get is 2 times 9.8 minus times 1,000 minus is v final squared is 19,600 meters squared per second squared. There's a square there. And so v final is plus or minus 140 meters per second. How nice that it came out perfect. I literally just made numbers up. Now, again, it's plus or minus. We have to consider what is it actually doing. And if you note, the position goes from large positive x to 0. That is a decrease in position in displacement. The displacement's negative, and the velocity vector is pointing downwards. And so we're going to take v final is minus 140 meters per second. Now, there's other ways to do this. You don't have to rely on just that number, right? So there it is, so you can read it for a second, right? And there's the solution we think we have. Maybe we want to check it. We're going to use the stuff that we calculated to check that it's consistent. Basically, we're checking that this time makes sense. And so we at least want it consistent. If we're wrong, it's got to be wrong in the assumptions, not in the math. So what we'll do is say, oh, we know v initial, v final is what we want, acceleration and time. We can do v final is v initial plus at. Right? That's how they're related. And these are all in the y direction. And so we'll have 0 plus minus 9.8 meters per second squared times 14.3 seconds. And v final y will be, when we calculate it, 9.8 minus times 14.3, and we get 140, and this is at 5 sig figs, but we only really need 2. So we're going to go with 140 meters a second. All right, we're just rounding. And it's negative, right? The number that come out was negative because we put in negative 9.8. So we get the right velocity. That's good. Now that we have the velocity, and what I'm going to do is very quickly write in here the initial velocity that we had. V initial x is v final x is 250 meters a second. Just so we have it on the page with us. That was a statement from the problem. Well, now what we have is, all right, we have a triangle with two sides. All right, this is v final y, and we have v initial y. So let's draw that. The x component is going to be fairly long, and it's going to be 250 meters per second. And then the y component is going to be a little smaller, right? It's going to be just over half this, and it'll be 140 meters per second. That's our two components. And what we want is, this is our v final. This is the direction of things going when it hits the ground. What we want is the angle. Maybe we want the actual final velocity as well. We can walk through that very quickly. It is v final is square root v final x squared plus v final y squared. square root 250 meters per second squared plus 140 meters per second squared is, so we'll do that, 287 meters per second. Yeah, and that makes sense. Falling objects should gain speed. But now we want the angle. And what we have, this is our opposite side, or our y side, and this is our adjacent, or our x side. And so tan theta is opposite over adjacent, which is y over x. And so we can do inverse tangent. We can get rid of this. So f theta is inverse tan, and then we put in our y and our x. 140, there's a minus sign because it's downwards, and 250, and then we put in units, which will cancel. But the important thing is that it's negative. So when we put it in, if hopefully you can see the calculator, we're doing 140 negative divided by 250, and we get a negative number, that's about right. And then we do the inverse tangent, and we get minus 29.2 degrees. So what that's saying is that in our original picture, when we draw in the collision velocity, we have the x direction, and this should be 29.2 degrees. Now, you could be trying to express this from the positive x-axis, which is this angle. And if we want to express that angle, it's going to be plus 360. So this ends up being our number plus 360 is 330.8 degrees. And then we would round that to 331, I guess. But that's the gist of it, is we've got, we're measuring either below the x-axis or above the x-axis and all the way around. But this tells us the direction. And whenever we want the direction that something is moving, we're going to work with the velocity, and it's going to be inverse tangent of y over x. All right. So hopefully that's enough video on that problem. We'll do some other problems, but this is a common sort of problem, is where is the thing going? And this is a common sort of type of problem to solve, is, if you have one direction, what is the other one that you need? So we will do a different problem in the next video.